Me again. Let's start with the next talk. Before I do that, let me just give a few more sentences about the last one. So one thing that I want to mention is that we actually proved something a bit stronger than I promised when we were proving this Johnson-Lindenstrauss thing. I told you that the way I'm constructing this JL matrix is that I'm choosing each entry to be independent random Gaussian variable. But what we proved is that as soon as every entry of my matrix is a sub-Gaussian random variable, those matrices will satisfy the distributional Johnson-Lindenstrauss and therefore the Johnson-Lindenstrauss. So in particular, if you want to create, why did we prove it? Well, all I used about the entries of my matrix is that this thing is Gaussian and Gaussian square is sub-gamma. But really, if entries Ti were sub-Gaussian, then this inner product would be sub-Gaussian with the correct parameter, and a sub-Gaussian variable squared is sub-gamma with the same kind of parameter. And as soon as you know those two things, then you could just go over the entire proof, and you can show that whenever you have a random matrix with independent sub-Gaussian entries, it satisfies this Johnson-Lindenstrauss. And this is cool because, for example, if you just choose entries to be plus minus 1 over square root d or something like this, they are sub-Gaussians, so this is a Johnson-Lindenstrauss matrix. And computationally, those matrices are much easier to work with than trying to draw a random Gaussian at every entry and then multiply by those. So a bottom line is that if you want to construct this Johnson-Lindenstrauss projection, all you need to do is for each entry you have to flip a coin. And you put a plus or minus 1 there, and you rescale it correctly so that the expectations are correct. This is what we proved. And also, this lower band that someone asked me about for why this dimension log n over epsilon square is necessary is by Gerani Nelson and Kasper Green-Larsen. Yes, also the slides are on the conference website right now. So if you want to try to follow what I'm talking about, you can try to download the slides, and or if you want to look at them later, which I doubt you will. Okay, let's try a new one. Is it working? Perfect. So we will prove in this talk another result that is kind of similar to this Johnson-Lindenstrauss business. Let's now imagine that, let's say that I have three parameters, k, epsilon, and delta, and I have this, again, this high-dimensional space, and there is some k-dimensional for k much smaller than the d, some low-dimensional subspace sitting there. What I want to do is I want to find I'm going to say that matrix, like a dimensionality reduction matrix from dimension d to m is a subspace embedding for the space V if it preserves all the norms of vectors in this subspace. Now, the fact that those things exist isn't as surprising as the original Johnson-Lindenstrauss, right? Because I could just as well, if the target dimension is smaller than k, then obviously you can do this. If target dimension is larger than k, then you can just look at the orthogonal projection on the subspace or whatever. So for a given subspace, it's obvious that you can find a subspace embedding of it, a linear map that preserves all the norms of vectors on this subspace. What is cool is that there exists a single distribution script D that does not depend on the subspace, such that with high probability over this distribution for any subspace V, we actually preserve all the norms of all the vectors on this subspace. And we can do this by reducing dimension from the dimension D into dimension about k over epsilon squared. And in fact, so we will be proving this theorem. And in fact, what we will show that whenever I have a distribution of matrices that satisfies this original Johnson-Linden stuff, so it preserves a single vector, norm of a single vector with a huge probability, then I can use the very same distribution and just adjust the target dimension accordingly and get an oblivious subspace embedding. So note that here I'm preserving a norm of, like all the vectors in the subspace. So there's infinitely many of them. I couldn't just use the Johnson-Linden Strauss as it is. It requires a little bit of cleverness. And why would I want to do this? One application that's, I guess, most interesting is, again, the sketch and solve. Imagine that you have a linear regression problem that's extremely over-constrained. So you have only k variables. You have only k variables and equations, and let's think that the number of equations is much larger than the number of variables. And you want to solve the linear regression, so you want to find the x that minimizes this L2 norm, or L2 norm square, whatever. So naively, if you want to do this, you will spend time about nk squared. You will do some sort of linear algebra. This takes time nk squared. Can we do something faster? And it turns out that if my matrix P is a subspace embedding for the span of the columns of A and the vector B itself, then I can just multiply all of those on the left-hand side by P, by pi, and I can solve this sketched much smaller regression problem. So in this regression problem, I'm going to have only order of k equations. What is not too difficult to show is that as soon as my matrix, sketch matrix pi, satisfies like this subspace embedding condition for this linear subspace, then whatever solution I get for this smaller compressed version of my problem is actually already a decent solution for the original problem. So I can speed up a linear regression in this extremely over-constrained setting. Well, I could speed it up. So now solving this regression problem is going to be much faster. I can do this in time k cubed, basically, as opposed to nk squared. If n is huge, this is a great improvement. Unfortunately, just the sketching part, just computing this matrix P times A is going to require, take nk squared time. So by itself, I didn't do anything particularly smart. Interesting. I used to have more of this slide. Better. Okay, so by itself, I didn't do anything smart, but it turns out that there are much better Johnson-Linden Strauss matrices than just random sign matrix. So there are matrices that satisfy this distribution and Johnson-Linden Strauss properties and have this additional property that I can perform matrix vector multiplication in time linear in the size of the matrix, as opposed to, nk squared or whatever. So if I choose matrix pi from a nice family, nice distribution that satisfies this distribution on JL, I can actually do the sketching in time linear in the size of matrix A. So I'm going to have a near linear time algorithm for the regression problem in this extremely over-constrained setting. Specifically, the time is going to be near linear in nk, say nk log k, plus something like k cubed or something like this. But if k is much smaller than n, I can speed up linear regression. So in order to speed up linear regression, we need to do two things. And we might do two of those things or one of them. One is to show that whenever I have a distribution of matrices that satisfies the Johnson-Linden distribution and Johnson-Linden Strauss, so with high probability it preserves a norm of any single vector, then in fact I can use this to get this oblivious subspace embedding property. So for any k-dimensional subspace, I can use the same distribution to project into something of dimension k over epsilon squared and preserve all the norms of vectors on this subspace. And again, the important thing about this subspace embedding is that I have a single distribution that does not depend on on a subspace V. So this is the first step. The other step is trying to show a family of distributions that satisfies the Johnson-Linden-Strauss, but also that come with an algorithm to do the sketching in time near linear in the actual vector that I want to sketch. We will see how it goes. Let's focus now on the subspace embedding business. So here's the plan of the proof. All I know about my favorite distribution is that it preserves norm of any fixed vector. So by union bound, if I have just a finite set of vectors, I could hope to preserve a norm of all those vectors. I'm going to define a thing called an AlphaNet or alpha covering. And so this is a geometric object. If I have some set B, I say that the alpha covering of a set B is just a set of points such that every point, so set of balls of radius epsilon that cover the entire set B. So set of points such that for every point in my set B, there exists something in my alpha net that's close to it. Okay? This is the alpha net. So what I'm going to do is, first of all, I have this subspace V, k-dimensional, and I want to show that, I was told that I should be using this, right? Yes? The script M. So this is just a name for this AlphaNet. So M for me is just some subset of B, and I'm saying that this subset of B is an AlphaNet for B. So here that would be just a set of centers of those balls. I'm going to say that this set M is an AlphaNet if for any point in B there exists something close in M. The point being that even though B itself is just like, some continuous set, it has infinitely many points, it will have a finite alpha covering. So I can cover this set B, which is, the set B with a finitely many balls of radius epsilon. So what we will do is, let's imagine that you have some subspace V of dimension k. And we want to show that a random map, or map that satisfies Johnson-Linden-Strauss, will actually preserve all the distances in this subspace, all the norms of vectors in this subspace. Let's look at the sphere, just L1 sphere, restricted to the subspace. So all the vectors in the sphere that has norm exactly 1. And let's find some covering of the sphere. And so I'm covering the sphere, I'm finding a finite set so that everything on the sphere has something close in my covering. By close, I mean just 1/10. Like the distance between, for every point in the sphere SV, I want something in this set MA to be within distance, say 1/10. And what I will show that those kind of sets exist and they are of size exponential in k, so 10 to the k, let's think. Once I've shown that, so now I want to restrict myself to this finite set. I want to say that, so since I'm working with a finite set, I can use Johnson-Linden-Strauss and I can say that my matrix actually preserves all the norm of the vectors in this finite set. When I'm using target dimension that's logarithmic in the size of the set, which is proportional to k. I'm going to need a little bit more. So what I'm going to show is that if all I know about my Johnson-Linden-Strauss matrices is that they preserve norms of those vectors, they also have to preserve all the inner products between pairs of those vectors. So for every pair of the vectors in my sphere, when I'm using a Johnson-Lindner-Strauss matrix, with good probability, the inner product after sketching is the same as it was, plus minus some epsilon. Now, all I need to do is to show this for some finite set of 2 to the k points. So I can hope to do a union band. I can hope to do this using Johnson-Lindner-Strauss matrix or with target dimension k over epsilon squared, for example. And then the final step is to show that since T is linear, as soon as it preserves all the inner products in this AlphaNet, so I have covered my sphere with small balls of radius 1/10, and I know that for each of those points, I'm actually doing pretty good. I'm actually preserving their norm and all the inner products fairly well. I can deduce from this that, in fact, for all the vectors whatsoever on my sphere, the matrix T preserves all the norms up to a little bit larger distortion. Now, here is an interesting part. I don't need the granularity of this net to depend on epsilon in any way. So, we could think that this epsilon is a very small number. It's enough to choose some constant alpha that's smaller than something. 1/10 is fine enough for all possible epsilon. So I choose alpha equal 1/10. I'm getting a single net of size 11 to the k, something exponential in k that doesn't depend on epsilon. And I'm saying that as soon as I'm preserving all the norms of points and the inner products, but this is not important. Let's just think of it as preserving all the norms of points in this net. Then I'm actually preserving all the norms of the points in the entire sphere. This will follow from linearity. So this is the high-level idea for how we want to prove this oblivious subspace embedding. And actually, all of those steps are pretty cool. So let's try to start with the first one. I have a k-dimensional sphere, and I want to cover it with And I have a k-dimensional sphere, and I want to cover it with balls of radius 1/10. So I have a sphere of radius 1. I want to cover it with balls of radius 1/10, and I want to prove an upper bound on. I want to show that there exists covering which doesn't have too many balls. I can cover it with only something like 10 to the k balls. How do I prove it? I'm going to introduce a new concept. So we've had this covering numbers or AlphaNets or stuff like that, which means that which are about covering set B with the balls of radius epsilon. There is a dual concept which is called packing numbers. So here, again, I have a set B, and now instead of using as few balls as possible or putting as few points as possible that will cover the set B, I want to put as many points as possible such that each pair of points is separated, so that points are far away. So in other words, if I put balls of radius epsilon over 2 here, I want them to be disjoint. And the P of B alpha is the so-called packing number, is just the size of the largest possible set of points within B that are alpha separated. So that such that each pair of points is alpha far away from each other. On the other hand, the script n of B alpha is a covering number, is the size of the smallest alpha net for B. And we'll see that those two numbers are related with each other. So first of all, this is easy. Whenever I want to say that the packing number with the distance 2 alpha, which is upper bounded by covering number with distance alpha. Why? So whenever you have, I want to say that in fact any covering gives me an upper bound on a size of any possible packing. So if I have a covering with, p balls, then I couldn't possibly pack more than p points that are 2 alpha away from each other, because I have a covering with n balls. I couldn't possibly pack more than n points that are 2 alpha away from each other, because if I had tried to pack more than n points, then at least 2 of them would fall into the same ball here, and if they fall into the same ball here by a triangle inequality, their distance is at most 2 alpha. So this is this inequality. Any possible covering, not only the smallest one, is an upper bound on every possible packing. But on the other hand, I want to say that the maximal packing, not even, say the largest packing, but in fact any packing to which I cannot really add anything more, gives me upper bound on the covering with the same parameter alpha. Why is that? Let's imagine that I have a packing of balls, and is maximal, which means that I cannot add any more. I cannot add any more point here, because it would then, like, a ball centered here would not be disjoint with whatever I have. So for any point, I cannot add a ball centered in this point. This means that this ball wouldn't be disjoint with something, which means that distance from the center to the other center would be bounded by alpha. So there is some change of the parameters here. I have, depending on how you define things, I think those inequalities are correct. But the point is that the covering numbers and the packing numbers are basically equal up to constant change in this parameter alpha. So any covering gives me an upper bound on any packing, but maximal packing by itself is already a covering. So if I have any maximal packing, I have an upper bound on the smallest possible covering, because I know that, well, maybe they are better, but at least this one is a covering. So the smallest possible covering couldn't be larger than this. So what we wanted to show is that there exists a small covering of a ball, a k-dimensional ball or a k-dimensional sphere with the distance 1/10. The way I'm going to do this is, instead of actually constructing a covering like this, I'm going to prove an upper bound on maximal packings. I'm going to show that every packing, whenever I'm trying to pack balls of radius alpha or alpha/10 in my set B, I couldn't possibly pack more than so many balls. If I prove an upper bound on this packing number, it will tell me that the covering number is smaller than something. So it will tell me that there exists a covering of my sphere with few points. Okay? Any questions? Let's try to prove it. So what I really wanted to prove are those things for this, like those covering numbers for an n-dimensional sphere, but let's just prove it for the n-dimensional ball, or n+1 dimensional ball. If I manage to cover n+1 dimensional ball, then I have already also covered the border of this ball. I can just project or something. This is not particularly interesting. So what I want to say is that I have a high-dimensional ball of radius 1, and I want to cover it with as few as possible balls of radius 1/10, or alpha. I want to say that there exists a covering with 1 + 1/alpha to the n balls. And in order to show that there exists such covering, I'm going to show that every packing doesn't have too many balls. So how do I prove this? I have my high-dimensional ball B2 to the n, and I'm trying to pack as many as possible. I'm trying to upper bound how many balls of radius alpha I can pack in this ball. You know, how much, like, it's not quite packing balls inside of this B2 to the n, just because I'm trying to find a set of centers. It might be that some of those balls will be, you know, a slightly, like, I'm trying to find a set. In this definition of a packing, I said that I'm trying to look for a set of P subset of B, such that each pair of points is far away from each other. But it's not necessarily the case that the entire ball centered at a point in P is inside of my set B, right? So I haven't really packed them inside. I might have those kind of balls that go slightly outside of the set B. But up to this, it is packing. So in particular, whenever I have a packing like this, some packing P like this inside my ball, this actually means if I just like stretch this large ball by some small alpha. So I look at a ball with slightly larger radius 1 plus alpha. I look at this ball. Now, all of the balls centered at those points in P of radius alpha are actually legitimately inside my larger ball. Okay, and they are disjoint. So now this is very legitimate packing. Like inside a 1 plus alpha times a B2 times a ball, I have packed a bunch of L2 balls of radius alpha. And I want to upper bound how many of those balls could I have possibly packed? So this is just like writing down what I said. So those balls, for any point P, a ball of radius alpha over 2 centered at P is contained in my original ball that's with slightly larger radius, 1 plus alpha. And all those balls are disjoint. So I claim that I couldn't possibly have packed too many of them, just because, you know, like all of them have some volume. So the volume of their union, like they are disjoint, the volume of their union is just sum of these volumes. And this must be smaller than the volume of the large ball. Right? On this example, it's clear. Like each of those balls has some area. So the number of balls I've managed to pack inside this large circle is smaller than, well, I couldn't have possibly packed more than the ratio between area of this and the area of this. Right? I know that this union is completely contained in this ball. Those balls are disjoint, so the volume of this union is just a sum over all the p's of volumes of those balls. All of those have the same volume, which is, you know, I don't really know what is the volume of high-dimensional ball. You can read this in Wikipedia, but I don't really need it, because all I need to do is, you know, this is saying that whatever packing I have, the size of the packing times the volume of this ball of radius alpha is smaller than the volume of a ball of radius 1 plus alpha. You just, you know, divide things by each other. The size of a packing is bounded by the ratio of the volumes of a ball of radius 1 plus alpha by the same kind of ball, except with radius alpha. Now, you don't really need to know what are those volumes. All you need to know is what is the ratio of those volumes. So I have a ball in a dimension n of radius 1 plus alpha or 1 of radius alpha. The volume of a ball scales with the radius as, you know, radius to the n times some constant factors. So this ratio of the volumes is just 1 plus alpha over alpha to the n. So we know that any packing actually couldn't be possibly larger than this 1 plus 1 over alpha to the n. And this implies that there exists a covering which is using only as few balls. Okay, so that's it for this step. Any questions here? Excellent. Now the second step. So now I have a sphere. And so I proved, as I said, I proved a covering of a ball. And now I'm going to say that I have a covering of a sphere. It's basically, you just cover a ball of dimension 1 higher, and then you project things or something. It's going to work. It's not too difficult. Okay. So let's say that I do have this AlphaNet on my sphere. And what I know from Johnson-Lindenstrauss is that as soon as I use a random matrix with a target, so my size of my set M is k over epsilon squared. And what I know is that as soon as I start, size of my set M is 10 to the k. I know that as soon as I start using dimension that is logarithmic in the size of this M, I actually preserve up to 1 plus epsilon all the norms of vectors in my net. I want to say that I actually have something stronger. Not only do I preserve all the norms, I also preserve all the inner products between all the pairs of vectors. And it's not, yeah, this is the simplest and most boring part of the argument. You just observe that you can express the inner product in terms of the squared norm of a sum and the squared norm of a difference. So this is just an equality. So really, if my, what I want to say is that if my Johnson-Lindenstrauss map not only preserves norms of u and v, it also preserves norms of u plus v squared and u minus v squared. For each pairs of vectors u minus v, u and v, then it is going to preserve inner products up to an additive error now, not a multiplicative one. So if T preserves this and this, then the distance between inner product of u and v and the inner product of tu and tv is going to be something like epsilon times this plus epsilon times this, which is bounded by epsilon. So I'm actually like, I have constructed this net of size something 10 to the k. I'm going to apply Johnson-Lindenstrauss for all pairs, for all vectors u plus v and u minus v for all pairs of vectors uv in this net. But since the target dimension depends only logarithmically, I'm not losing anything. I'm just going to apply the JL for 10 to the 2k vectors or 100 to the k vectors. But log of this is again on the order of k. So the bottom line is, if for all pairs of points u and v in my net, I have a linear map that preserves multiplicatively u plus v squared and u minus v squared, then it's going to also preserve up to additive error inner products. Okay? And we can get this with a Johnson-Lindenstrauss that has target dimension k over epsilon squared. All right, now all we want to do is extend. So now we are going to use a linearity. We want to say that if I have this net, whatever the size of this net is, if I have this net on my sphere, it was called M, and I know that I have any linear map whatsoever that preserves all the inner products between points in this net, then this linear map actually must preserve all the norms of the vectors on the entire sphere. Okay, so how do we do this? So let's take some vector v naught on a sphere, and I want to show that this vector that norm of TV naught square is close to V naught square. Well, all I know about my map T is that it behaves well on the points on the net, and I know what a net is. So I know that for my point V naught, there exists some point pi naught that is close enough to V naught. So I can decompose that V naught is equal to pi naught plus the remainder, whatever is the difference. And I know that the norm of this guy is actually small. So this is V naught minus pi naught is actually small. So now I'm going to look at this remainder R naught. So I'm going to look at this remainder R naught. I'm going to rescale it so that it's back on a sphere. And since it is on a sphere, there exists a point that's close in my net that's close to this rescaled guy. I'm going to call it pi 1. So this thing here is V1. V1 is again on a sphere, yes?
Can you raise that up so we can see it? It's covered by the podium.
I see. No, I cannot. Let me try to rewrite it.
What was the labeling on the points inside the circle? One was V naught, the other one was...
Let me try to rewrite what I just said. Okay, so I have some arbitrary point V naught that is in a sphere. I know that there is a guy pi naught that's close to it. So I know that V naught is pi naught plus the remainder. And I'm going to define V1 to be just whatever is this remainder, but rescaled back to a sphere. So divided by its norm. This point V1 is again on a sphere. I know that I have a net on this sphere. So there exists some point pi 1 such that pi 1 minus V1 is again close. Smaller than 1 over 10. I can do the same trick with V1. So I again decomposed R naught into a small factor times something in a net plus a remainder multiplied by something much, much smaller. So I do the same thing for V1. V1 is equal to pi 1 plus the remainder. If I plug this back in here, I'm getting that V naught is pi naught plus some scaling times pi 1 plus some scaling gamma 2 times the remainder. Where the remainder is again of norm 1. It's on a sphere. I can decompose it into something that's on my in my net plus the remainder. The important thing is that because I knew, so what are those gamma i's? They are just, like gamma 1 is basically the distance between V0 and pi 0. Gamma 2 is this distance between V0 and pi 0 times distance between V1 and pi 1. So if you just plug those things back in, you will see that gamma I actually drop exponentially. So I can continue this process as long as I want. And for any point on the sphere, I can decompose it in the following way. I have a sum of points pi k in a net times some scalings. Those scalings drop exponentially, plus another scaling times some remainder. And this is And I can continue this as long as I want, so I can make this term as small as I want, and norm of vk is always 1. Any questions here?
V1 equals remainder R naught divided by what?
The remainder R naught divided by its norm.
By what?
By norm of this remainder. So this is the same as here. Remainder v naught minus pi naught divided by the norm so that it's back on a sphere. Now, since it's back on a sphere, I can find some pi 1 in the net that's close to it, and I can decompose it as v1 is pi 1 plus its own remainder. If I plug this back in here, I'm going to get that v naught is pi naught plus gamma 1, whatever was the scaling, times pi 1, plus gamma 1 times the new scaling times the remainder. For the new remainder, I do the same thing. So I'm getting a sum of the points in the net with the coefficients that drop exponentially and a remainder that has, again, a coefficient that's exponentially small in which term in how long I have continued this process. Okay, so this is pretty cool, right? Now I can just choose to continue this process as long as I want, and if I want to compute the norm of TV, L2 norm of TV naught, I will be able to express it in terms of inner products of points in my net, plus some remainder that's hopefully going to be small enough so that I won't care about. And for inner products of points in my net, I know that my map T preserves them. Let's try. So what we have? We have this decomposition. I can choose whatever k I want. I have a decomposition that V naught is the sum of rescaled points in my net plus a remainder times the exponentially small coefficient. And I know that for each pair of points in my net, the inner product between t times pi I and t times pi j is as it should be plus minus epsilon. So what is the L2 norm of TV naught square? Well, this is, you just apply t, and this L2 norm square is, inner product of this with itself. So you expand the square. You have that L2 norm square is sum over all I and j of gamma I times gamma j times the inner product, plus whatever is maybe 2 times the remainder, right? Because here and here, like on both sides. That's nice. So now we know. So what is the difference between this and actually V naught square? From all those terms, I'm getting that the difference is bounded by epsilon times the gamma I, gamma j. So V naught square is this expression. V naught square is the exact same expression, except that I don't have t here. I look at the difference, and I do know that the difference between this inner product and this inner product is at most epsilon. So, okay, so I just take the difference. I have that in this part, the difference is bounded by gamma I times gamma j times the epsilon. And I have to sum it over all I and j. And in this part, I can do something crude. I know that my map T has some sort of norm. So, like this inner product is at most norm of T square times, those things are norm 1. Vk and V naught are norm 1. So this whole inner product is at most norm of T square. The same inner product without T is just at most 1. But I know that I have this extra gamma k plus 1 coefficient that I can make as small as I want. Because I could continue this decomposition chaining process as long as I want. So if I choose to continue it for so long so that this gamma k plus 1 is much smaller than alpha over norm of t squared, whatever norm of t was, this entire term is going to won't matter at all. So all I care about is that this norm of tv naught minus tv naught squared minus v naught squared is epsilon times the sum over all I and j's of gamma I times gamma j. And let's say that I just upper bound this by, sum up to infinity. I know that all of those terms actually drop exponentially. So this thing sums up to a constant. And because I chose alpha to be as small as 1 over 10, it's easy to say that this thing sums to a constant that's smaller than 2. Questions? Okay, so I guess, yeah. So I guess the clever part is just doing this decomposition. Once you've managed to do this decomposition, you notice that what you need is actually to preserve all the inner products. You see that this works, and then you do the calculation and see that actually, since you preserve all the inner products in the net, you preserve the norm of vector v naught as well.
So gamma I is given by alpha to the I?
Yes, exactly. So in each step, I'm getting, I'm multiplying my coefficient, but by something that's smaller than alpha. And yes, for me, I chose alpha to be 1 over 10. That's why I have this 1 over 10 here. Yeah. Okay. So this actually finished the proof of the oblivious subspace embedding part. Right? Yeah, I guess that's it. We'll finish 10 minutes earlier. If you have any questions,